Hey guys, let's wrap up the lesson we had in class with the Bohr model. And let's think back to pre-AP when we learned about the atomic spectra of hydrogen. We did this around flame test. You may have a memory of doing the flame test labs, and we looked at through the diffraction grating glasses, and we were able to see these atomic spectra. Today's activity was supposed to give you a chance to look sort of behind the scenes more than we were able to do in pre-AP and figure the math behind these colored lines. So in the atomic spectra of hydrogen, we pass light from the hydrogen source through slits, and then it can be diffracted either with a prism using refraction, or we can actually pass it straight through diffraction grating. Either way, we can split the light from a hydrogen into its components, different colors, and on the screen we get the atomic emission spectra. And in pre-AP I mentioned how each of those lines correspond to a particular transition of the electron in the hydrogen atom. And so we talked about this, the Bohr model, that as electrons absorb energy, they go up into their excited energy states, the higher orbitals. And as they relax and fall back down toward lower energy states, they give the photons back off. It's some form of energy. It doesn't have to be visible light, but a lot of times it is. Now I'm looking at the very back page of the Bohr activity, where it says, now construct a graph using the data from tables 1 and 3. Make energy the dependent variable on the y-axis. And then that means we're going to have, we don't really care about what's on the x-axis. And we're going to draw arrows to represent the transitions, electron transitions from table 3. All right, so let's see what we can do here. We have a pretty wide range of numbers to go on the y-axis. So this is our energy. And we did have it in kilojoules, just keep that in mind, per mole. All right, so what I'm going to do is I'm going to make the first energy level be my sort of baseline here. So 13, 12 is what I calculated for the value of energy level 1. We'll make that there. And then I'm going to kind of do the little squiggly come up a bit. The next one we have was, let's start counting at this point by 100. So let's make this negative 400. And then let's make this negative 300. And then negative 200, negative 100, and so just for some reference, I'm going to put 50 here, and then let's put 25 here. All right, so again, we had some weird, a large scale here, so we got to do the best we can. Energy level 1 was all the way across the bottom, so that's going to look like our x-axis. And then energy level number 2 had an energy of about negative 328. So about right here. And then for energy level number 3, I calculated negative 145. So that's about in this neighborhood. And then negative 82, so that's about right here. And then negative 52, so about right here. And then negative 36, so about right here. And then 26, and we're really starting to get jam-packed. And then negative 20, basically right on top of it. And then it just really keeps getting closer together. And I'm not drawing that one nearly close enough to represent how close together they are. So then we move on to table 3, and we want to use arrows to represent the assignments that we gave it. So the first one, 97.25 nanometers, comes from an assignment of 4. So just keep in mind, this is level 1 to bottom, 2, 3, 4, 5, and so on. So the first assignment was for 4 to 1. So boom. And what we've represented here, the horizontal lines represent the energy levels of each shell, the amount of energy an electron has when it's on that shell. And then this transition, this arrow, sort of like a vector in physics, where it represents the magnitude of the energy change. You can see that's a very large energy change. And then the next one would be from 3 to 1. And then a 2 to 1. So there we see quite a cluster of some pretty energetic changes. That is meant to show you a photon possibly with a high energy. And if you looked on your EMR spectrum, you would see that those 3 you most likely classified as UV, with the first one being on the border of X-ray. So we move to the next group. We have 8 to 2. That's what I calculated it at. So let me make sure I count my lines. 4, 5, 6, 7, 8. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8. So way over here, and I'm going to come down to 2. Now that looks like a long way, but if I had drawn this really a much better job to scale, that long arrow really, I'm not sure is even as energetic as the 2 to 1, this arrow that we did right here. They're pretty close though. All right, and then we have a 7 to 2, which is going to be from here, so less energetic. And then 6 to 2. And then we had a 5, a 4 to 2, and then finally we had a 3 to 2. So we can see that as we drop those lower, as we get closer and closer together, the drops, the arrows get smaller, which means less energy given out. Okay, and then we had a series here starting at 8 and only going down to 3, and then from 7 to 3, 6, 5, and then 4. So we can see a cluster there of even smaller changes. And then I think at the very end we had a 5 to 4. I did it correctly. So at first glance, this may not look like much to you, but I want you to see a couple of things here. Obviously, first of all, we have some clustering of the arrows as the electrons have a certain landing spot. So this first cluster is they're just landing on level 1, and then here they're landing on level 2, landing on level 3, and so forth. And even then, if they're all landing on the same spot, doesn't necessarily imply they're all going to have the same energy, because it also is determined by where they started from. If you didn't get this drawn, hit pause real quick and sketch this out on the back of your paper, and then we'll move on when you're ready. This is a similar graph to what we just kind of sketched out from our own calculations. The energy unit's a little different here. This is in electron volts, but the idea is the same. You can see that we have some distinct clusters of lines here. And these distinct clusters of lines end up being what you actually observed in the atomic spectra that you did back in pre-AP. We saw from the hydrogen spectrum the Bohr series, which was the colored lines. Let's take a look at even another graph here. So this is, again, is similar to what we just accomplished, just different units over here on the y-axis. But we can see we have these very large energy transitions that are so energetic they give us UV. So we don't really have, follow this arrow over here to the very bottom of the spectra, our eyes can't see those. But if we had UV glasses on or some kind of UV detector, we could be able to see a series of bars. But from the hydrogen spectrum I showed you in the very beginning of this presentation, we saw the red, the green, and then a couple of the violet lines. And you trace their arrows back to their origin, and you can see it comes from this middle section of transitions of the electron that ended on energy level 2. So when, for example, if an electron was excited up to 3, level 3 in the hydrogen atom, and then fell back to 2, that change in energy was equal to a photon that is in the red range of the EMR spectrum. And that's where very specifically that red bar came from in the EMR spectrum. And then here, if you fell from 4 to 2, that's the electron transition in hydrogen that gave us that greenish, kind of a blue, greenish cyan kind of colored line. And then we have an indigo and a violet as well. But that's very specifically where those transitions came from. Now, just like the UV that we couldn't see, there's also some infrared that we couldn't see. If we had infrared detectors or glasses on, then we would see more bars out here for the transitions of the electrons that landed on level 3. And let's go back now. We have different names for those. The Balmer series is the ones that we can see. The Balmer series was discovered before Bohr made his model of the atom. He actually made a model to fit the observations of these atomic spectral lines that Balmer came up with sometime before Bohr. So they've been known for a very long time. The UV has its own, it's called the Lyman series, and then the IR is the Paschen series, and then there's actually a microwave radio called the Brackett series. So it all depends again on on what energy level does the falling electron stop, and 2 or B, from where do they start. And the larger that fall, the more energetic the photon that you give off. So just to kind of wrap it up again, here we see the helium spectrum, and we see the Balmer series of lines for helium. We can see a bright yellow color in the middle. That's going to correspond to some electron transition of about, level 5 to level 2, something like that. It's a very strong line, so if we look over here at the wavelengths, you go to your EMR spectrum, it's probably going to be this 501 here. I guess it could be the 447. No, that's too high. It's probably the 501. Remember, the longer the wavelength, the lower the color. So this down here is going to be your red, 667 nanometers. And then up here is going to be your violet, the shorter wavelengths. So that yellow one's going to probably be right here, 501. And we would see, like I said before, we'll see the same thing in the UV spectrum. There would be separate vertical bars representing those electron transitions if we had a detector to put it into a range that we could see. All right, I hope that makes sense. If you have any questions about the purpose of this particular activity and learning the number values behind the spectrum, come by and ask.